I'd like to welcome you to the UW Paul Allen School's Distinguished Lecture Series. It's my great pleasure and honor to introduce today's speaker, Liz Spelke. Liz is professor of psychology at Harvard University, and she's one of the pioneers in the area of developmental psychology that really investigates how infants and young children acquire and develop knowledge about the physical world around them. She's done some really fascinating studies, for example, in how infants over time develop a better and better understanding of how objects should behave when they are in front of them. So, for example, even questions like an object should not or does not disappear just because you can't see it for a moment, or objects, for example, shouldn't randomly change their color and their shapes. And again, she's done some really fascinating work in that area, and you might now wonder why here in computer science. And it turns out that this work is becoming more and more relevant even for a lot of work in computer science, especially in machine learning, AI, and robotics. So for instance, in robotics, when we work on robot manipulation, the traditional approach has always been that we assume that we have very accurate models of the world. We know the shape, the masses of objects, we know the friction of the surfaces, and if you know these parameters of the world, then you assume that you can actually get a robot to pick up objects and move them around, and everything is going to be easy because we have these really, really good physics models of the world. It turns out that these models don't really work well on a real robot in the real world. They work well in simulation, but as soon as you try them in the real world, they really don't work anymore. And there is now a new approach, or where more and more people are looking at kind of alternative representations where maybe we can get robots that don't have these exact physics models of the world, but rather sloppy, intuitive models or an intuitive understanding of how the world works. So for example, if I open my fingers here, nobody would be surprised that the microphone falls down. Things like that, right? And that, of course, now asks questions about how do humans develop this kind of knowledge about the world, how the world works. And today Liz is going to share some thoughts on her research in this direction. Welcome, Liz.
Thanks to you. Thanks to everybody, students and faculty who met with me today. I've had a hugely good time here and found all sorts of interesting areas of connection that my children would never have dreamed I would have found, me being one of the least likely people to ever be able to navigate my way around a computer. But behind, of course, all of the work with computers that many of you do are questions about the nature of intelligence and the nature of knowledge that I think actually unite us with psychology. And those are the kinds of questions I want to talk about today. I actually want to talk in particular about one question that I'm hoping in my old age we may even make some significant progress in answering over, say, the next 5 or 10 years. And let me set it up by focusing on the creatures that I would direct this question to, that is to say, human children from birth until about the age where they start their formal education at about 5 years of age. Now, I submit that over this 5 to 6 year period, children are displaying the most remarkable general purpose intelligence of any entity known to us, human, machine, or anything else. Before anybody ever starts trying to explicitly teach them anything, they are developing encyclopedic knowledge, common sense knowledge about the world around them. They're learning the language of their society. They're learning the basic categories into which people classify objects when we talk about them or reason about them. They're developing all of the basic skills that you need to get around in the world as a child, and with just a few exceptions as an adult. They're learning all of the cultural products of their society, its songs, its rituals, its art forms, its norms, and its beliefs and values. And they learn all of this stuff without anybody explicitly teaching them any of it, simply by making their way around in the world and observing other people and interacting with them. Now, what makes this particularly remarkable is not only that children's knowledge, that the knowledge that children gain is rich, but that the knowledge that they could have gained had they been born into a different culture differs from that quite dramatically in lots of ways. So every human culture has some form of visual art, of music, of technology, systems for measuring things, measuring space and time and abstract qualities like value, and belief systems like knowledge of mathematics or science or ethics. Every society has some such system. But if you look from one society to another, or you look within our own society across historical time, what you see is enormous changes in the specific things that we know. And yet children could have been born into any of these different societies or at any different point in history, and they would have learned the local culture. So this sets up my question. What this suggests is that children are capable of developing comprehensive, common sense knowledge, not only fast, but flexibly. So what is it that allows their knowledge to be both fast and flexible? We know something about how to get creatures to learn things quickly by restricting greatly the set of options of what there is to learn. For example, in a classic study of imprinting or learning to avoid a food that will poison you. And we know how to get lots of animals to learn things flexibly by allowing them to learn slowly, taking in enormous amounts of data. But children seem to learn both fast and flexibly. So how are they able to do that? Answer, we don't know. It's a great unsolved problem. But I'm talking about it because, as I said at the outset, I think it's a solvable one. And I think that we can make some headway towards it by doing the sort of things that I do, behavioral experiments on infants and children. I'm here, though, because I also think that the sorts of things that I do will not be sufficient to solve this problem on its own. I think it's going to require a vast interdisciplinary enterprise. And within that, we're going to need behavioral research not only on children, but on animals, undertaken from a wide variety of different perspectives. We're going to need research not only on behavior, but also on brains. And I think we're going to need research in all of the disciplines that led to this invitation. Research on in artificial intelligence and machine learning and diverse areas of the computational cognitive scientists to ask not only what kids can do, but what kinds of operations are going on in their minds when they're doing it. Now, in return, I hope that research on children's learning might be able not only to gain from computer science, but maybe to give a little something back to it along the lines of what Dieter was suggesting in his introduction, suggesting some avenues that might be interesting to explore computationally, taking as a starting point some of the feats of learning that we see in young children. So what I want to do today, my talk is, I think, in 3 parts. I want to start out by talking about infants and some of the things that they seem to know right at the beginning when they first start learning about the world. Then I want to talk about just one example of children's learning, a change that takes place around the end of the first year of life. And then finally, I want to share with you a hypothesis to explain children's learning that I think has a chance of explaining children's learning, I hope in this case and in others, and end by sketching how I think that hypothesis and other rival hypotheses might be tested through this interdisciplinary enterprise that I think we could all engage in. So what do infants know? This is a question that over the last 50 years or so, lots of people, including Andy Meltzoff and Patricia Kuhl here in this room, lots of people have been addressing through research on human infants. And I think that research provides evidence for core competence in at least 6 different domains. One, which Dieter was talking about, basic core understanding about certain properties of objects that allow babies to pick out objects in perceptual arrays and predict or understand under certain conditions what they're doing and what they're going to do next. There's also core knowledge of people as agents who act on objects and by acting on them cause changes in them. There's core knowledge of a different aspect of people's ability to experience the world and engage with other people and communicate those experiences to other people. I call that core knowledge of persons. There's core knowledge of places in the environment and the acts of navigation that can take you from one place to another. There's core knowledge of forms that becomes really important when kids start categorizing objects as members of different kinds, which I'll talk about later. And there's core knowledge of number, approximate numerical magnitudes. It falls far short of the number concepts kids need to have in school, but I think it provides a partial foundation for them. Now, all of these core systems have, I think, some interesting and rather peculiar properties in common. One peculiar property is it's quite intuitive, I think, to think of the brain as a set of peripheral systems for sensing the world and forming initial interpretations of what's out there, for acting on the world, and then a single central system of beliefs. But I actually think that core knowledge systems are situated both above the peripheral systems and below our explicit conscious, statable beliefs about the world. They occupy a middle ground between sensation and perception on the one hand and explicit belief on the other. And more particularly, they do so because they have a set of properties in common that I'll be trying to illustrate today. First of all, like systems of belief, the core systems center on abstract interconnected concepts. So each system functions as a whole, and at its center are some very basic general abstract properties of the world. I've listed here for you to peruse what I think the key abstract notions are at the center of each of these systems. Now, the second striking property is that core knowledge systems are profoundly limited. They're extremely limited in what they cover. I could take the person system as an example. On the one hand, it centers on these abstract notions of capability of having phenomenal experiences and of sharing experiences in states of engagement. But if you ask babies, and babies come into the world expecting there to be entities out there with those capacities. But if you ask a baby, what should a person look like? At birth, they would not distinguish between the face of a human being and the face of a monkey, or the face of a sheep, or the face of a bird. Okay? Very, very little specific knowledge about what people look like. Also, we'll see very little specific knowledge about what people can do. So general knowledge about the abstract properties of other social beings, lacking, but highly limited in its specifics. Third general property of core knowledge systems, they activate specific systems in human and animal brains. Again, I could use the person system as an example. When we are in states of engagement with other people, or when as third parties we observe other people in states of engagement, that activates a particular region in prefrontal cortex, in the middle of prefrontal cortex, which is a signature of that system. In adults and also in infants, recent research shows. These systems are shared by other animals and therefore are ancient. When I say they're shared by other animals, I don't just mean we are able to, human infants are able to represent objects, and other animals, including infant animals, are able to represent objects. I mean that when we look at detail, at the abstract concepts at the center of the systems, the limits to those systems, the brain systems that are activated by those systems, we see the same systems across different animals. I think this is the reason why most of what we've learned about human brains has come from studies of animal brains, because fundamentally the earliest emerging systems seem to be the same across us and other species, and therefore very ancient. They emerged in ancestors who were roaming the earth long before we were. Now, because these systems exist in other animals, we can ask about the role of experience in their development. That's very hard to do with studies of human infants, because we're both ethically and practically limited in the ways in which we can manipulate the experience that infants are getting. But with non-human animals who show the same abilities, they can be reared under controlled conditions. And when you do that, you find that systems for representing entities in each of these domains, for representing persons, for example, are present and functional at the time of the infant's first encounter with another human being. So in this case, at birth, right, where they come out of the womb and they're first in a position to engage with other human beings. And similarly for each of these other systems, at the time when infants first face the task of navigating through the environment, the system of place representation is already present and functional. Now, in addition to being innate, these systems emerge early and remain present throughout life. Studies of adults reveal, especially when we look at people's implicit abilities while they're focusing on some explicit task, we're asking, are we also seeing activation of these systems? And you see signature patterns showing these systems that are at work in infants also continuing to function at older ages. And the systems support children's learning. So those are the general properties, but I've laid them out for you without giving you a shred of evidence for any of them. So let me try to switch, because I do experiments, from general claims to data and talk about just one of these systems, the agent system, and use that system to illustrate the first two properties. Then I'll turn to a different system to illustrate the rest of the properties. So reasoning about agents. Before getting to what's core to the really young infants, let me tell you a little about a lot of experiments that were done in different laboratories asking how infants starting at about 6 months of age are able to reason about other people when they see them acting on objects. The first thing that those studies reveal is that infants expect people and other agents to be able to move, to set other objects in motion, but only when they contact them. So if a person moves behind a large door-shaped occluder toward a stationary object, and after the person's fully hidden, that stationary object starts to move, infants infer that the person contacted the object. And you know that from experiments where you remove the occluder and allow them to watch events in which the two objects either come into contact or the first stops short of the second and then it starts to move on its own. Infants look longer at the latter event, providing evidence that that was novel for them. That was not what they expected had been going on when the occluder had been present. So they expect agents to move objects on contact. By contrast, they don't hold that expectation if an agent is moving toward another agent. So agents can interact with one another at a distance. Second, agents' actions are directed to goal objects. So using the same method of repeatedly showing infants one event and then asking them what they expect to see by measuring how long they'll look, Amanda Woodward and many other people have familiarized infants with an event in which they see a person reaching for one of two objects in a single location, and then they test them by exchanging the positions of the two objects and asking, how new is it when the person reaches on the same trajectory to a new object versus on a novel trajectory to the old object? And infants look longer when the reach is directed to the new object, providing evidence that they encoded the original reach, not as a particular spatial temporal trajectory, but as directed to that goal object. Now, interestingly, infants do not show these effects if instead of presenting a person who's reaching, they present, what's presented is an inanimate object that's moved from off-screen on these different trajectories. So this is for agents, not for inanimate objects. Third, infants expect that agents can't pass through walls, and they will efficiently circumvent them if there's a wall in the path of some trajectory, some goal that they're attempting to achieve. So these are studies begun about 20 years ago by a group in Hungary where they familiarize infants with events in which a small object moves toward a larger object by jumping over barriers of variable heights, always jumping just a little higher than the barrier to get over. And then they take the barrier away, and the question is, what will the agent do next? Jump on one of those familiar trajectories or take a more efficient straight line path to the goal? And infants expect the more efficient straight line path in this case. Now, that doesn't, they showed that that doesn't just reflect a general expectation that people will that motion, or a general preference for motion motion on deviated lines rather than motion on straight lines, because you can make this effect go away very simply if you repeat the whole experiment, but now you present the obstacle that had been in their way so that it's actually behind the goal object. So the jumps that you now see are inefficient. And in that case, they no longer expect an efficient reach to the barrier, trajectory to the barrier at the end. Finally, at about the same age, maybe a little older, infants will have a further expectation about the sources of motion of an inanimate object that appears on a puppet stage from off stage and appears to sail over screens of different heights, always just moving high enough to clear the screen. Presented with these events, research by Rebecca Sachs showed that infants infer, because this is an inanimate object, they infer that there's an agent who set that object in motion behind the screen, and therefore they expect to see a hand come out from the side that the object came from, not the side of, that the object was moving toward. Now, interestingly, again, this isn't a general expectation that infants apply to everything. They only apply it to the motion of an object that they've seen to be inanimate. So if before this event begins, instead of presenting an inanimate beanbag, they were shown a puppet that was actually seemed to be moving on its own, now infants no longer expect that there'll be some agent off screen setting it in motion. In other words, they're attributing agents to causal powers to agents at 11 months of age. And given evidence that the puppet itself has the power to move itself, they no longer infer that appeal to another agent to account for its motion. Now, these properties of agents are interconnected. And I want to illustrate that with finally getting to an experiment from my own lab, which was conducted by Shari Liu a few years ago, using animated characters, which allowed us to get a lot of control over the nature of the events that we presented. So these animated characters are spherical bodies with winsome faces and human voices that don't actually use any language, but make, sighs and sighs of pleasure and other kinds of expressions. And what happens is infants are familiarized with 4 different events. In one event, this central character looks at a yellow triangular object to its left, and then starts to approach that object. And as it starts to approach, a barrier comes down. So it stops, backs up, looks to the top of the barrier, and then jumps over the barrier to the object. On another trial, there's a blue object that appears on the other side, and the same kind of event happens, jumping to that object. The other 2 events are the same as the first 2, except that the agent chooses not to jump. Okay? So he looks to the top of the tall barrier and then backs away and doesn't jump, and similarly for the middle-sized barrier on the other side. So over the course of familiarization, the babies see the agent moving equally often to each of these 2 objects and refusing to move equally often to each of the objects. The thing that differs across these is how high the barrier is, and therefore how high the agent will have to jump to get to the objects. And to see whether infants use this information about the cost that the agent is willing to undertake to get to the object as information about the value of that object for them, infants were then tested with simple events where no barriers ever appear. For the first time, the 2 objects are there simultaneously. The infant looks to both of them, and the question, the agent looks to both of them, and the question to the infant is, which one do you think he'll go to? So they're alternately shown events in which the agent approaches each of the 2 objects, and they look longer when he approaches the object for which the agent had previously taken the less costly action, providing evidence that they expected the more valued object to be the one that the infant had jumped higher to get to. Now, I'm talking about this in terms of cost, but of course there's lots of physical variables that distinguish the more costly action from the other one. The guy is jumping to a higher extent. He's moving on a longer path. We equated the duration of all these events, which means he was moving faster to get to one of the objects than to the other. And of course, it's of course possible from this study that any many of those variables were simply a direct cue to value for the infants. To try to get some sense of how plausible that story was, we ran 2 further experiments where, again, the logical structure of the experiments is the same, but the particular physical situations and the particular properties of the actions that the agents took differed. And they differed in such a way that no single perceptual variable would yield the same performance across these 3 different situations. Now, performance was the same, which I think gives us initial reason to think that what infants are doing here is not just learning about local cues to object value, but rather computing object value by appealing to some more abstract notion of cost. So that's at 10 months of age, which for people like me is ancient. Okay, and we tried and failed to do these studies, these particular studies with younger infants, because they require an awful lot of memory, right? Who was there, how high were they jumping, and so forth across the different familiarization events. But there have been studies done with younger infants, and they suggest, actually, that an awful lot of learning is going on over the course of the first 10 months of life, learning about agents and their actions. So in particular, in that situation in which I showed you 6-month-old infants will represent objects as directed to goals when a person reaches, will represent actions as directed to goal objects when a person reaches for one object over another. When those studies are repeated with 3-month-old infants, infants fail to represent the object as the action as goal-directed. Okay, so a 3-month-old infant, after you switch the positions of the 2 objects, will look equally at reaches on the new path versus reaches to the new goal. Interestingly, though, research by Jessica Somerville and Amanda Woodward showed that if you give infants a brief session where you put on them mittens that have Velcro attached to them that allow them to pick up objects on contact, and then you show them those events where another person wearing the same mittens is reaching for the different objects, now the infants succeed. Now, I should have told you that 3-month-old infants themselves are not capable of reaching for grasping and displacing objects. They sure look like they would like to be. So if you present them an object that's nearby, they'll kind of go like this, right? But should they actually happen to touch it, they will bat it away. This happens all the time, by the way. You can't leave a ball near a 3-month-old infant because they will want it, and every effort they make to get it will make it go further away from them. They can't engage in any kind of coordinated reaching. But this 1 minute long in some of the studies experience of wearing a mitten that sticks to an object and displaces it, first of all, they're completely fascinated by this. And second, after that happens, when they see that mitten on another person, they expect that they now encode the reaching the way the older infants do as being object directed. A similar thing seems to happen in the case of these events of jumping over barriers to get to objects. The earliest that the Hungary group was ever able to show evidence for this ability was at 6 months of age, and that led Amy Scarry in my lab to wonder whether this was a case as well where sticky mittens might be useful. So she ran an experiment on 3-month-old infants where now she presented them with videotaped events of a person reaching over a barrier to an object. They were familiarized with that and then tested with events in which the barrier was removed and they either reached straight to the object or circumvented it. And all of these were preceded by 3 different conditions of action training. One condition was no training at all. Babies simply come in and view these events. A second condition was training with a person wearing mittens, just like the person in the video, but the mittens didn't have any Velcro on them. So the baby could wear the mittens and feel like, oh, I'm like that person on the video, but if they tried to get the object, they would just bat it away. And the third condition was the sticky mitten condition. And just like in the Somerville-Woodward reaching studies, the sticky mittens condition was the only one that worked. So when they actually were able to pick up and displace this object by themselves, they now expected the agent who picked up the object, that agent would reach on a direct course if the barrier in the way, once the barrier in the way was removed. Now, why did they do that? We considered 2 possible reasons. The first and sensible reason was the infants themselves in the sticky mittens experience never faced a barrier, but they did have the opportunity to approach the object on a direct path. So maybe they simply came to expect that the other agent would use a direct path, come what may. That if that's what they expect, then they're going to look longer at the circuitous path on the test events. So to test that, Amy Scarry ran a second experiment. And in this experiment, she randomized babies. All of the babies got the sticky mittens, the effective mittens condition, and she randomized them to 2 different conditions. So in one condition, it was just a replication of what had happened before. They saw the agent reach over a barrier. The other condition was identical, except the barrier was never in the way. It started out behind the object, and then in both conditions, it disappears at tests. So the conditions are the same for the test events. So the idea was, if babies simply expect straight line movement across the board, then they should behave the same in these 2 conditions. But as you can see, what she found was success in the condition where there had been a barrier, failure in the other condition. So it looked like somehow this reaching experience was leading them to expect efficient action only when the person had been reaching over a barrier rather than on a blatantly inefficient route during the initial familiarization. But that raises an interesting question, I think. What was the mittens experience doing for the 3-month-old infants? They themselves didn't have any experience circumventing barriers. There were no barriers on the display when they were wearing the mitten, touching the object and getting to move it around. Well, a hint at an answer, I think, comes from a little discussed finding from the research on sticky mittens in the situation that Somerville and Woodward, the situation I began with and that they studied. They discovered that the effect of the mittens on perception of goal-directed action only occurred if they were watching an actor who was also wearing the same mittens and reaching for the same object that the infant had been reaching for. When the study was repeated with an actor who wasn't wearing mittens or an actor who was wearing mittens but reached for a different object, then the mittens had no effect and the babies failed just as badly as they did with no mittens training. So this led us to think that maybe what's going on here is not that babies are developing some understanding of how you reach for and pick up objects. Reaching may be as profoundly mysterious to these babies after the mittens training as it was before. When they see somebody touch an object from above and somehow manage to lift it in the air, they may have no clue how that happens. And actually, visually, it's far from apparent in simply watching someone else how that happens. When they try to do it themselves, as I've said, they're utterly unsuccessful. So they may be mystified by that action. But there may be another action that they do understand, the simple relationship, the causal relationship of action on contact. What may happen is that wearing sticky mittens turns an otherwise inscrutable reaching event into a much more easy to understand contact event where you simply touch an object and it moves on contact. Well, that led to a prediction and our most recent experiment, and I'll end this series with it. This is another experiment by Shari Liu, just published. The prediction that it tests is that if the effect of mittens is to turn a complicated reaching event into a simple case of action on contact, then it should be possible to get success out of a 3-month-old infant without giving them reaching experience, simply by giving them visual information for this causal relationship of action on contact. So to test that, Shari presented infants with the following, let me see if I can animate it, following event. Now, there's supposed to be a soundtrack with that. When she touches the object and it lights up, it also makes a noise. And the noise and the light continue as long as her hand is on it, and then when her hand moves off, they go away, okay? So nothing, no pickup, no biomechanically complicated stuff going on, just touch the object and it makes a noise. So babies saw that event repeatedly with reaching over a barrier, and then they were tested with the barrier removed, and the person, again, reaching and making contact with the object, reaching either on a direct path through the space where the barrier had been, or with the same arching indirect motion. And the babies looked longer at the arching motion, which was consistent with seeing the direct motion as expected, right? Expecting efficient reaching when the barrier was removed. Of course, it's also consistent with an intrinsic preference for the circuitous motion over the direct one. So Shari ran a second condition, which was identical to the first, except that the barrier appeared behind the screen. Actually, all of the studies I'm going to show you that Shari conducted were conducted with these same videos. They were just digitally altered. There was no barrier in there when they were filmed, and they were digitally altered to put a barrier either in front or behind. So we know that every other aspect of the motions were the motions themselves were identical. But when the barrier was behind during familiarization, the effect goes away. Okay, so it's not an intrinsic preference for the curvilinear motion. It's only when that was an efficient motion that they expect the efficient motion at test. Now, this is consistent with the idea that detecting a simple contact relation suffices. But to test that directly, Shari ran a third condition. And in this case, the original reach with the barrier was digitally altered in a different way. It was altered such that the finger froze, actually the whole hand froze, when it was a half second before the point where it would contact the object. It froze there, a half second passed, and then the object lit up and made a sound. To an adult, it looked like it was doing it on its own. So the familiarization event was identical in every other way to that of the original condition with contact. They equal in timing, equal in sound, and so forth. But there was this half-second difference in the visual display such that the hand and the object never came into contact. And now we had the sound with it. You couldn't really hear the sound of the ball, though. I'm sorry about that. Anyway, it started half a second after the hand stopped moving in midair. Now, in that condition, again, we did not see this effect. And there's a reliable difference between that condition and the original condition with contact. Because these are the days of reproducibility, Shari insisted, and I gave in, that we run a full replication of this experiment by randomly assigning kids to one or the other condition, testing them in a situation where there wasn't a single experimenter involved who knew which condition any given baby was in. They sounded the same, and they couldn't see the visual displays. And we replicated that effect. Okay? So it looks like at 3 months of age, before infants understand what reaching is, before they can pick up objects and manipulate them, they have interconnected abstract concepts of cost and causality, right? That under conditions in which an agent causes a change in the state of the world, they do so by acting on the object whose state they are changing on contact. Okay, so that's an example of the evidence that leads me to say that infants' understanding is abstract. Centers in each domain, centers on interconnected abstract concepts. And it also starts to show you the evidence that leads me to say that core knowledge is extremely limited in all of these domains. I've shown you some limits already to infants' understanding of action. They don't understand what reaching, young infants don't understand what reaching is, don't have any expectation that if there's 2 goal objects out there and you reach to one, that therefore you like that one more, you're more likely to reach to that one in the future. Don't get efficiency under the first conditions that we tested for it. Much later in development do they begin to start to understand the kinds of multi-step actions that underlie tool use, acting on one object so as to create the conditions in which you can act on another. So they know really virtually nothing of the specifics about how you act on objects. But they do seem to have this ability to represent objects and reason about them in ways that capture these abstract relationships at their core. So that's all I want to say about agents. I want to point out 2 more things, though, about core knowledge systems that you can see if you quickly glance at the abstract notions underlying understanding of objects compared to agents, and the limits to infants' representations of objects compared to the limits of the representations of agents. I think that in addition to being abstract and limited, each of these systems operates as a unitary whole, distinct from the other systems. So they operate under different conditions. They capture different properties of the world. Let me turn now to the other 5 general properties of core knowledge systems, and I'm going to go through them much more quickly, I think with just 2 slides, maybe 3, and using infants' numerical abilities as an example. So infants start responding to changes in number and to numerical information as early as you can test them. I'll tell you about one study conducted in a maternity hospital in Paris with babies in the first 3 days of age. For this study, experimenter went into the room that the babies were in, waited to find a baby who was awake, and started playing sequences of syllables to the baby. And for half the babies, each sequence had a single syllable repeated 4 times. So the baby might hear 2, 2, 2, 2, and then ra, 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 and then another syllable 4 times, and so forth. The other condition was the same, except that each syllable was much shorter, and they heard 12 syllables in a sequence instead of 4. And after listening to this for a minute, the auditory track continued throughout the study, but visual displays started arising one by one. And in alternation, the displays presented 4 simultaneously present objects or 12 simultaneously present objects. Now, studies had already shown, actually, Andy, you and Pat did one of them, that at older ages, babies will tend to look, given a choice of 2 events to look at, and a soundtrack that goes more with one of them than with the other, they will tend to look at the event that they're listening to that corresponds to the sound. So infants' looking time to these visual displays was recorded to see whether their looking was affected by the number of syllables that in each sequence that accompanied it. And in fact, in this study and a replication using different numbers, also in a 3-to-1 relationship, that's what they found, that infants looked longer. Infants who were listening to 12-syllable sequences looked longer at the array of 12 objects, and vice versa for the infants listening to 4. Now, interestingly, this system was shown to have the key property of these sorts of numerical representations that appears in studies of older infants, of children, and of people like us. Okay? That is that they're ratio limited. Now, a newborn infant's much less sensitive to ratio differences than an adult is. We could discriminate dots that differed by a ratio of 7 to 8 or even maybe 9 to 10. They require a 3-to-1 ratio difference to represent them reliably. But qualitatively, it looks like the representations are the same. And as I just said, these representations can be tested and found at all ages of human life. They activate the same. They activate specific region of the brain, and the same region is activated when you test infants and children and adults, and when you test non-human animals, which tells us both that there's a dedicated neural substrate, but also that this is an ancient system that we share with other animals. None of the core knowledge systems seem to be unique to our species. So it's an early emerging and ancient system. The one thing that this work doesn't show is whether it actually supports children's learning. I think there's some evidence that it does, but that question is still partly out. Let me quickly take you through the evidence. First of all, we know that there's a relationship between the precision of children's core number representations, their sensitivity to approximate numerical differences in displays like arrays of dots on the one hand, and their symbolic math learning on the other. For one thing, studies of the meanings that children assign to number words show that early in development, when they first start responding in a meaningful way to number words, they give them approximate, not exact meanings. Second, before children are taught how to perform symbolic arithmetic with exact precision, they're able to perform symbolic arithmetic with approximate precision. As long as they've learned the meanings of the number words, then if you give them problems like 21 plus 30, does that lead to a bigger number or a smaller number than 34? So you can answer the problem without doing the exact calculation. You find that children answer these problems, that the precision with which they answer these problems is predicted by the precision with which they would answer what's numerically the same problem presented as arrays of dots. Okay? So these are related to each other. We also know that numerical acuity for arrays of dots is correlated at every age that's been tested, including in adults up to age 80, I believe, research by Justin Halberta. It's correlated with people's mathematical abilities as measured by SAT quantitative scores or grades in school. But these, of course, are all correlations. Is there a causal relationship? Well, there's about 5 labs that have done studies in which they've trained kids on tasks that exercise approximate non-symbolic numerical representations. And I'll give you just one example from Dan Hyde, who presented babies in 2 conditions with arrays of dots that they either had to compare or they had to mentally add and then compare the sum to a 3rd array. And then 2 control conditions involving the same comparison or addition tasks, but not using number. And after a brief period of training, kids were given tests of exact symbolic arithmetic and of reading. The training with the numerical tasks led to enhanced speed and accuracy of performance of the exact arithmetic task, but not the reading task. So it looked like there's a specific representation there. These kinds of training effects have been found in a number of different labs. So at the least, we can say there's a short-term enhancement of arithmetic performance that comes from training of the approximate number system, but no evidence from any study that I know of in the lab showing that children's development of new numerical concepts is enhanced by exercising this system. And I hope I have time to return to that at the end, because that's something I think we're now starting to understand, but not based on these kinds of methods. Okay, so summary so far. I've taken you through each of these different properties, except for the last one, which I'll leave a little question mark on for now. There's evidence, I think, for all of these properties with all of the core knowledge systems. And what I want to suggest is that there's a reason that we see all of these properties hanging together when we do studies of the cognitive abilities of infants. The reason I think they hang together is that I think there are deep reasons why they hang together. And the key property that I think connects them all is the fact that these systems are ancient. So let me see if I can convey this reasoning to you. The ancient origins of these systems implies that there's some very distant ancestor, perhaps 300 million years ago, in the case of systems like the object system and the agent system and the number system, all of which seem to be shared across humans and birds. Okay? So an ancient ancestor. Between that ancestor and us, for that system to have persisted, it can't have been tied to the specific perceptible properties of the animal's environment, because many, many diverse, different species of animals have inhabited many, many diversely different environments in that span of time between when that ancestor was walking around on Earth and when we're walking around on Earth now. So any properties of what an object looks like, what a navigable layout looks like, what home looks like if you're a navigating animal and you need to get back there, any local specific perceptible property that worked in one environment likely would fail to work in later ones. So new mechanisms would have to evolve for dealing with that changing world. But when cognitive systems center on highly abstract properties, the thing about those abstract properties is if they're true of one environment, they're true of all of them. So every navigable layout is going to be approximately Euclidean. Every animal is going to be capable of causing its own motion and by moving, causing changes in the world. Every object, whether large or small, whatever it's made of, is going to move. If it moves, it will move on spatiotemporally connected paths. These abstract properties will apply in all environments. So when we find a system is ancient, it's going to be abstract and it's going to be limited. It's not going to be capturing things like what's the difference between what a human caregiver looks like and what a chick caregiver looks like. Okay? Second, over that course of evolutionary time, there's going to have been an enormous amount of change in the brain. Now, if a cognitive system weren't neurally localized, if it were distributed across the whole brain, then as whole new systems develop, as we get our neocortex, for example, that's likely to interfere with the functioning of the ancient system. But if the ancient system is relatively encapsulated, then it could, in principle at least, survive changes in other parts of the central nervous system. So I think ancient and enduring brain systems that function robustly are likely to be encapsulated. Now, any system that depends on abstract properties is going to be hard to learn. So if these ancient systems center on abstract properties, there's going to be pressure, I think, for them to emerge to not require experience for their emergence, because if they required experience, they'd require a lot of it, because the information for these ancient properties is so subtle. And finally, because ancient abstract properties apply to all environments, they're not only going to be useful at the beginning of the learning process, they're going to be useful to us throughout our lives. So there's no reason for them to simply be scaffolding that we find in infants that doesn't persist later on. However, children's uniquely fast, flexible learning can't rest on core knowledge alone. So let me pivot at this point to talk about the second half of this talk, how I think children go beyond core knowledge. First, a couple reasons why core knowledge can't be the whole story. It's entirely shared by other animals, but no other animal engages in that rapid, flexible cultural learning that we see in humans. It's limited, core knowledge is limited, but if anything is true of the concepts that children learn in school, it's that they can, in principle, apply to anything. We can learn whole new domains of knowledge as humans. Yeah, I think those are the main reasons that we need something more than just core knowledge. So that then raises the question, how do children go beyond core knowledge and gain the capacity to acquire all of the common sense knowledge that develops over the first 5 years? So what I want to do is, I'm going to present you with a hypothesis, not an answer. And I'll do so by focusing on just one developmental change that occurs at the end of the first year, and that I think yields two new kinds of concepts simultaneously. One, a new concept of people as both agents and social beings at the same time, social agents, and a concept of objects as members of kinds. And to introduce these, I'm going to talk about yet another study that I get no credit for, a study that was done by Fei Xu and Susan Carey some 20 years ago now, actually a series of studies that were done by them, followed by a line of studies simply by Fei Xu and her students at Berkeley. And I think I've got them all on one page. The situation is very simple. There's an occluder, and from behind that occluder, an experimenter brings out an object, say a shoe, and then returns it behind the occluder. Then the experimenter brings out another object on the other side, say a rubber duck, and returns that behind the occluder. And now the question for the infant is, how many objects are back there? And to get an answer to that question, the occluder is removed on alternating trials. There's just one object, or just the shoe, let's say, or two objects, both the shoe and the duck. And infant's looking time is recorded. And the findings are, depending on the age of the infants, we see a change. 10-month-old infants are neutral on the question whether there should be one duck shoe behind the screen or whether there should be two objects. 12-month-old infants are not. They expect two objects. Now, interestingly, they went on from there to ask, what happens at intermediate ages? And they found that at 11 months, some infants expected two objects and some didn't. They asked a whole bunch of questions of their parents, and the best predictor of who was going to behave like a 12-month-old were the parents' reports of whether they knew they knew the names of these kinds of objects. Kids who knew the words, whose parents said they knew the words duck and shoe, were more likely to succeed than those whose parents didn't. So then Fei, in her own lab, did a glorious series of experiments with 9-month-old infants, where now, instead of relying on the infant's knowledge of language and ability to spontaneously generate knowledge, she simply relied on the degree of language comprehension that a 9-month-old infant has attained. We know that starting as early as 3 months, infants become sensitive, actually at birth. Based on prenatal experience, they show some sensitivity to specific properties of their native language. By 6 months of age, they respond to relations between a number of the most common words and their visible reference. And so she's dealing with 9-month-old infants now. And she found that by labeling them, either with the correct names or with nonsense words, but in a syntactically legal context, like look, obligate, look, atoma, she could flip them from representing, from failing this task to succeeding. When she used 2 different words, they succeeded on this task. When she used a single word 2 different times, they did not, okay? So the use of language in this task flipped the kids. Now, it wasn't simply the production of distinctive sounds, because when she said ooh and ah to one of the objects and made 2 negative sounds to the other object, that did not flip them. It was only the sentence, look baby, obligate, or look baby, atoma, right? Either a real word or a nonsense word that led to success. Now, in further studies, she showed that babies not only expect 2 objects when they hear 2 words at 9 months, they expect those 2 objects to have different forms and functions. And I won't take you through the studies that showed that, but basically, you look into a box and give 2 and say, look, obligate, look, atoma. They expect to see 2 different things. And if you act on them, they expect you to act on them in different ways. If you just say, look, obligate, then they don't expect 2 different things. In fact, they have the opposite expectation. So what's language doing in this case? Here's my hypothesis. I think these words are appearing in noun phrases whose meaning comes from 3 different systems of core knowledge. A cup is a physical body in the object system with a dedicated form that was created to fulfill a specific function. They may not know about the creation part at this point, but a dedicated form and function. Now, look, on the other hand, is a verb. And it's a verb that invites a state of social engagement or shared experience, okay? It's coming from a person. And that, I think, is activating the person system and inviting the child to communicate with this person, sharing an experience of this object. Now, when look is combined with the first phrase, cup, it suggests there's one interesting shareable experience of an object that they could share together. When it shifts to a different word, their language is indicating there's a different experience that they could share, maybe an experience of a different object, maybe an experience of an object of a different kind, or with a different shape, or with a different function. But the language that people are using, not because they're trying to teach infants anything, but simply because they're ordinary speakers who obey natural language pragmatics. That language is giving infants information about how many things are out there and what their properties are. And in particular, it's giving them an interesting piece of cultural or sociological knowledge that people consider the distinction that's marked by the different noun phrases they're using in a single context to be important, to be worth saying. If they didn't think that that was an important distinction, they would use one word for both of them. Okay, so generalizing this hypothesis, I think what learning a natural language may give children is a unique system for composing new concepts from core concepts. And that ability comes from, I think, a number of 3 properties of this system. That any natural language has an open-ended lexicon. It's got a relatively small set of rules for forming expressions by ordering the items in the lexicon. And the rules depend only on the grammatical form of the lexical items, not on their meanings. So as far as meanings go, language allows you to combine anything with anything else, giving extreme flexibility. And it has a compositional semantics. This is the part of natural language that I find most mysterious, but it's self-evidently true. when you learn a new word, you become able to understand not only the sentence in which you learned that word, but infinitely many other sentences that you can compose using that word. The meanings of the expressions come from the meanings of the words, together with the rules for combining them to form the expression. Finally, I think a critical property of natural language is the way that speakers use language. They use language to speak economically. They use it to be informative. Good speakers don't tell you things they think you already know, and to be relevant to the situation. Now, I think these properties allow children to learn new words rapidly, not just by ostension. And most of word learning isn't happening by ostension, by pointing to some property in the word, some entity in the world that word names. Surely the first object names are, but most of language is not. Most language is learned by introducing words in sentences that you otherwise understand. So if you understand a sentence like, I've got a dog and a cat, you can go a long way toward learning the meaning of the word to, or the meaning of the word pet, or any number of other abstract terms, just by working out, by the way the other words in that sentence constrain those meanings. Now, the fourth property, the pragmatics, is what focuses children, I think, on the concepts that adults find most useful and appropriate, which is why, I think, these rules of language not only aid children in learning language, but in learning what the significant things are in the world that people are inclined to talk about. So I think language learning is supporting rapid, productive, flexible concept learning for this reason. And I see people are leaving, which tells me I'm out of time. Is that true? I'm out of time. OK. I won't tell you about our kind concepts or why the arguments against language as the key to our cognitive flexibility are wrong. But what I do want to end by coming back to a point that I started with, and which brings me back also to why I was so happy to receive this invitation to be able to come and talk to you, which is I presented you with a hypothesis. The key question at this point, I think, is how could we test this hypothesis and rival hypotheses to discover what it is that makes children such fast and flexible learners? Okay? Now, I submit that we can't test any of these hypotheses using the kinds of experiments I have spent the last hour telling you about on their own. These experiments are really good ways of figuring out what children know at the particular time that you're testing them. They are not in themselves very good at finding out how they know what they know or why they know those things and not other things. And what causes their knowledge to grow. And this is why I think it's so wonderful that there's now interest in an interdisciplinary enterprise that tries to marry these kinds of behavioral experiments to work in other disciplines. And the three disciplines that I'm most excited about are the ones that those of you who've been hosting me are engaged in computer science. Also work in neuroscience, focusing on functional brain imaging, and I spent a really nice morning learning about, at iLabs, right? Learning about some of that. And finally, field experiments in education. So if you'll bear with me, I want to give you one slide on each of those. First of all, computational work. How can efforts to build smart machines provide us with insights into how children learn and vice versa? Let me give you just one example of an insight that I got from Tomer Ullman, who was building machines to engage in naive physical reasoning. The programs that he was working with are generative models that are capable of simulating events in which objects move through space in accord with basic physical constraints. And he proposed that infants core knowledge of objects in infancy may depend on something like the programs in video games and computer animated films, physics engines that simulate the motions of objects to make realistic looking physical events. He pointed out that the programmers of physics engines don't build in all of physics, and they don't build in full representations of the objects whose motions they're simulating. If you need to render an object, you need a detailed representation of its perceptible properties, but that doesn't need to be inputted to the physics engine. You can economize a lot by simply representing an object as a body of indeterminate shape, color, other properties in a particular location with a particular mass. Now, if you do that, then it's possible that the infants in the shoe and carry experiments are economizing in similar ways. They're tracking objects behind an occluder, not holding on to the distinctive, not by simulating the movements of the detailed distinctive properties of the duck and the shoe, but rather just blob going in here, blob going in here. And that can account both for their successes and for their failures. Now, further extensions of this work are exploring how the kinds of simulations that are generated by physics engines together with graphics engines might be able to train feed-forward networks in the brain to get them to recognize objects by their shapes, to get them to engage in common sense physical reasoning. Work looking at simulations in other contexts makes similar points about navigation, how systems that simulate paths through the environment might train the brain to prepare it for the task of real navigation in the environment, a task that an animal has to be able to succeed at the very first time they navigate. With that, they can't learn it by trial and error, or they will not survive. And I'm tempted by the idea that prenatal simulations from generative models that we inherit from those distant common ancestors may account both for how infants are able to show sensitivity to abstract properties of the world the first time they encounter an object or an agent or a place in the environment, how they're able to do that, and also why they might be so insensitive to the more specific properties of those things that you need perceptual systems to detect. I think these could underlie the expressions of core knowledge. If that's right, how could we test it? Brain imaging, I think, could provide a wonderful way to test whether, in fact, infants in experiments eliciting core knowledge are simulating events. We know that distinctive simulation processes have been found in animals and in human adults in tasks of real and virtual navigation, respectively, simulation of paths through the layout. It should be possible to test for them in infants and to test for them in each of these core domains. Finally, on the causal question, I'm going to go really quickly here, but on the causal question, I think we need research of a different kind where we leave the lab and go into the field and look at children's learning on the time scales over which it actually happens, which is to say months and years, not the 20 minutes that we test them per session in my lab, and in the environments in which they happen, which is to say homes, preschools, daycare centers, parks, the noisy social environments in which children actually learn. But of course, we want that research to be rigorous. And so I'm very excited about new collaborations between psychologists and economists who go out into the field and both implement and evaluate interventions to aid children's learning. And I've been involved in a succession of 3 experiments in India that build on the core systems for number and geometry to develop games for kids to play to enhance their readiness for learning mathematics. Our first experiment was a colossal failure. I mean, a success in that the kids loved the games, a failure in that they did no better at math when they subsequently went to school. The second study did a little better, and the third one worked really well in government schools with teachers implementing it. So we're now going to be trying it in other parts of India where we can look more specifically at effects of language on children's math learning by comparing people who speak not only the effectiveness of the games in people who speak not only different languages, but languages with fundamentally different ways of representing number and other properties. So just to end, let me come back to my original question and 3 general challenges, I think, for the study of intelligence in general and human intelligence in particular. One, can we understand the minds and brains of children deeply enough to be able to build machines that learn like children do? I'm hoping that the answer is yes, and that the effort to do so will bring us both better machines and a better understanding of how children learn. Second, can we understand how knowledge grows in young children's minds well enough to design better ways to teach them? I'm hoping through field experiments and other things that progress can be made there too. Though the first lesson I see from randomized controlled experiments in education is how important those experiments are. Because our initial intuitions about what's going to work almost never turn out to be right. And the first experiment in any domain of education almost always turns out to be, I think, a disappointment. And then finally, here's one that I'm inspired to throw out for people living in Seattle. Lots of interesting new stuff being developed around here. Can we come to understand our own minds, both as they develop in children and in us as adults, well enough that we can start making intelligent predictions in advance about what kinds of new technologies are actually going to be good for us, make us happier, make us function better, make us smarter, and what kinds of technologies are going to get us into trouble. And for any given technology, how can we design them to make them truly useful, a useful addition to our immense cultural repertoire? Okay? I think these are all questions that we could answer. We haven't done so yet. I think it's a really good time to try. Thanks.